Meet AI Series 7. My name is Lara from Cocoon Networks and I'll be your host for tonight. So our co-hosts for this evening are Emotech, who are a fantastic London-based AI startup, and they've developed Ollie, the smart home robot, who has the ability to learn from his owner or owners over time and starts adapting his personality to suit theirs. So that's, I find, pretty fascinating. Emotech, in turn, has been named one of the top 14 European startups by TechCrunch, and Ollie has raked in 4 CES 2017 Innovation Awards, so he's doing very well. Lovely, and our next co-hosts for tonight are Neurotech X. They are a non-profit organization with 17 chapters all over different cities in Europe, North America, and they are a strong global networking community. They provide key resources and learning opportunities, and they convene researchers, hackers, enthusiasts, and experts. Now, Meet AI, this monthly series, what we hope to achieve together with Emotech is to provide you guys with some latest insider knowledge and insights into AI, to create a vibrant community here that people feel excited about and learn new things every month, and just provide insight into cutting-edge theory and practice and get the best people at the forefront of the field to deliver their newest ideas. Now, the panel discussion tonight will be dealing with the past, present, and future of machine learning and neuroscience. So we'll be looking at collaboration and the achievements and the limitations of these industries. Now, we have fantastic panelists tonight, which I'm very excited to announce. Our first panelist is Grace Lindsay. She has just completed her PhD at the Center for Theoretical Neuroscience at Columbia University. Can we give her a round of applause, please? There you are. And then our second panelist of the evening is David Valeriani, I hope I'm saying this right, who's a postdoctoral researcher in brain-computer interfaces at the University of Essex. There we go. Welcome, David. And then we have our third panelist of the evening, who is Warwick Roseboom. He is a time perception group leader at the Sackler Centre for Consciousness Science at the University of Sussex. Round of applause, please. And moderating this panel will be Javier Asensio, who has completed a PhD in brain-computer interfacing at the University of Essex, and he'll be taking over from here.
So, well, thanks everyone for being here tonight. It's a lot of people. I think we are all that we are supposed to be here. Thanks to, of course, Cocoon for allowing us to do the event here tonight. It's an incredible place to do it, and of course for the beers and snacks. Also, I would like to thank to Emotech for co-organizing this event tonight, especially to Julia. She's it's been an exceptional co-organizer. Well, and thanks to our panelists, but they're going to be in an incredibly interesting conversation tonight. Well, that's what I hope. I'm taking my to-do list. You already have introduced Neurotech, so that's great. In every event, I like to ask how many people from you guys come from academia, have a research background. Okay, that's quite a lot. So that's good. Tonight, of course, we are not in an academic conversation. We are trying to engage the public in machine learning, neuroscience, and science in general. So we will try to keep that approachable as possible and don't talk with technicalities, but with broad concepts, so we can communicate them better. So yeah, that's it. Machine learning and neuroscience. So there are two trending topics nowadays, right? Well, specifically, neuroscience has been a trending topic since it was starting to study, since we humans started to study how the nervous system works, right? Machine learning, on the other hand, has been a hot topic for the last 3 years, 5 years, outside of academia, of course. So, whereas neuroscience focuses on studying the nervous system, the brain, machine learning tries to give this ability to computers to learn by themselves, right? So you don't need a programmer to tell the computer how to solve a task. The computer will learn by itself how to do it. I was really excited to be able to set this tonight, to organize this event, because the relationship that you can find between neuroscience and machine learning. I come from an engineering background. I feel quite obvious, you know. So you have neuroscience that has things to do with medicine, biology, and then you have machine learning. So let's try to make things together. So obvious example is you have a bunch of MRI data or MRI images, and then you train something to look for tumors, and you are able to diagnose tumors quite easily. On the other hand, you may have data from EEG readings. So you put an electrode to a brain, you get data, and then you train a classifier to control a computer using that data, which is great. And that's an obvious relationship. But the relationship between these two topics is way more deep, and they're really entangled. So around 70 years ago, these two lads, McCulloch and Pitts, decided to create a model. So McCulloch was a neuroscientist and Pitts was a logicist. Do we have any logicists here tonight? No? That's what I thought, like no one is a logicist anymore. So they come up with this model of a neuron. So it was a really simple model. You have a bunch of numbers, you sum them together, and if the result is higher than a threshold, this cell activates. Quite simple. So that's the basic. It was the first model, the first metaphor that computer science took from neuroscience. It exploded from them. If you add to the mixture things like gradient descent learning, you add processor multi-layers, you start having an algorithm that is able to learn and mimics somehow how the brain works, right? It's been a long time since then. Now, instead of these artificial neural networks, we call them deep neural networks, or deep learning, which is a really fancy way of saying humongous neural networks. So what we do is scale these structures many times, so they learn faster and better. So during the last 5 years, we had many breakthroughs, especially in computer vision. And the reason why we had these breakthroughs, or one of the reasons, is not only because we have the capability to build bigger networks, because we have bigger computers and faster, is because we start mimicking how the brain works. So especially in computer vision, we started to actually create the same structures that we have in the visual cortex, what processes our brain, how our brain processes images, and we implemented them in a computer. And suddenly we are able to recognize faces and tell that there is a chair or a dog, which is interesting. Not only that, also how we pay attention to our the stimulus in real life. So now I'm seeing all of you, but my eyes are jumping here and there. So if you implement something similar to a computer, this computer vision algorithm is going to be way faster, and it's going to consume less resources. So that happens also. Something that we take from evolution in our brain, right? But not only that, because that seems that, computer science is taking a lot from neuroscience, but it works the other way around. One of the interesting topics that we're going to cover tonight is this study from Warwick, that they use a neural network to understand how the brain perceives time. And they're using a artificial neural network, the same that we use in order to classify cars and dogs, to measure this time perception, how we perceive time as synonym as a biological entity. So this is just the surface. In general, these two fields are starting to make incredible breakthroughs, but we are way far from the latest goal that would be like completely understand how the human brain works, right? And this is quite interesting because if you think about it, if for us to understand how the brain works, we need to build one brain, right? So we can actually see how the different parts connect to each other and understand how the whole system works together, which is something that's being done in projects like the Human Brain Project. And for this to happen, we need to improve the machine learning, because without machine learning, we won't be able to simulate this brain. So we are in this cycle of these two sciences that need to work together in order to achieve something as important as that, right? So, okay, this is one of the best moments of the night, because it's when I shut up and I invite our panelists so they can start the actual discussion. Thank you.
So I guess I'll start. So I'm Warwick, and I'm at the University of Sussex in the Sackler Centre for Consciousness Science, which is a strange thing to call a research centre, but that's okay. It's interesting that I'm here because I don't work on machine learning and I don't do neuroscience, but I kind of do a poor imitation of both. So I was just going to give you an introduction to a few of the recent projects that I'm doing very quickly to give you an idea of how, I guess, as we're talking about how we might integrate these two different approaches and get something more out of it. And that kind of gives you an indication of how people in my discipline, at least not machine learning, not neuroscientists, are doing a poor job of each. So the first thing I'm going to talk about is, well, overall, my talk will kind of be about the two ways that we've been using machine learning. Firstly, in regards to kind of partial models of perceptual or sensory systems, and then secondly, as kind of data reduction. So with regards to, as I mentioned, neural imaging data, for example, which is this huge amount of data, and we have to kind of get some interpretability out of it. So the first thing I'll talk about is these partial models and some work we've been working on with that. So at the moment, I'm working on this TimeStorm project, which is this large-scale EU project, and some collaborators of ours have these humanoid robots that aren't very good, and the goal is to give them this artificial, to give them a sense of time that matches humans, and so this supposedly would enhance their interaction. So if the robot that you're interacting with has some idea about how you're experiencing the passage of time in a scene, then you might have a more natural flow in interaction with it, is the idea. So this that I'm going to talk about now is all in this manuscript that's on bioRxiv if you wanted to get more detail about it, or you can just ask me about it afterwards. So many of you might know a little bit or a lot more than me about deep convolutional neural networks and the basic properties of them. But just as a very quick overview for those who don't, the basic idea is we can give an image like this puppy, and it'll go through this deep network, and through a series of connected layers, you end up with a classification category, hopefully dog. Dog is doing a good job, right? And so this is basic architecture of a deep convolutional network for image classification. One really neat thing about the way that these things are designed, it's not by accident of course, because they're inspired by biological systems, is that as you go through the hierarchy, with layer 1 being the lowest layer here, up to the highest layer being layer 5, there's this kind of complexity increase in the representational selectivity of the neurons in those layers. So you can see at the early layers, they're basically looking for spatial frequency edges and stuff like that. By the time you get to the higher layers, you're looking at objects like dog, house. And what's really interesting about this is it mimics really closely the hierarchical arrangement of biological vision, particularly in humans, right? So in layer 1 is very much like what we have in primary visual cortex in humans, so we're very selective to spatial frequency and orientation. And then as we move down towards basically temporal, or along the visual tract there, we end up with these more object selective cells, so they become more and more selective to more and more complexity. What we did was we took advantage of this to build our network that could generate some estimation of time. So we have again this hierarchical arrangement of selectivity of responding, and we just give it a frame of a video. So this is just a snapshot of one frame, and the colors here indicate the degree to which a neuron, it's a bit of a cartoon here, a neuron in the network at a given layer is responding to elements in this frame. So you might be able to see there's a cow appearing down there. So you might have, this is the cow cell. All right, it's the one that responds primarily to cows. So it's responding a little bit, and then of course we move on. Now there's a lot of cow, it's responding more, or so on. And what we can do is we can just take the distance between, to some distance between the activations in these different layers, between the successive frames, and we can basically get an estimate of how different or how same they are. We can then track that over time, so that's what we have over here in what we're calling feature extraction. So the black spikes here are indicating the distance at a given time point between a layer's activation and its next activation. And then if we just look at the red line, that's what we're going to call our threshold. We basically say if the black line, if spike there exceeds that red line, it's something that it matters. It's some perception that mattered to the system. It's some kind of perception that would matter to us. It's a salient change. No cow, cow. If you care about cows, that's a salient change in the scene. We can then just use a simple regression. So we just track the number of these salient events that occur over time, and we can just use a regression. We can get back an estimate in standard units of seconds, so then we can compare it with how humans might report it. To kind of validate how this worked, having built it, we showed it a bunch of different videos of different scenes. So these are around Brighton. This is in town Brighton, that's my office. On the campus, out behind campus is cows. And can you just press play on that? So this is basically all we showed. So we showed our human observers and our system, a video which just looked like this. Yep, that one. That's all. So they watched an hour of different videos, in this case, of watching a cow. In a minute, the person who has the camera, and it's like this egocentric point of view, so in a minute the person walks away and ignores the cow again. There's a whole bunch of different scenes. And so we just had our human observers come and watch these different videos, and they would go for some period of time, and then after it finished, we'd ask how long it went for. That simple. And then we'd also show the exact same video to the system as I just described it. No, one second. Can you just go back to the slides? Sorry. Okay, so here's some data that we got out of our experiment. So on the left here, we have our human reports. The x-axis here indicates the actual duration that the video went for, and the y-axis is the estimate. And so the line here is the average of the estimate of 50 observers that we had do it. The dotted line would be if they were doing it perfectly according to physical value. And then over on the right here, we have the different estimates that our system made under different configurations. Basically, all you can see though is that, especially under the gaze model condition, which we can talk about later if you'd like, our model was able to reproduce quite closely how the humans performed on the same task. So that's quite a decent validation. In the manuscript, we describe a few other cases that our data more closely matches human perception as well. But what this tells you is that if we start with this basic kind of kernel of a sensory system that might be looking something like a human sensory system, that is a deep convolutional network for image classification, we use that as the core of our model, so we can get at these second order or higher order kind of more complicated perceptual behaviors like time perception. We can do a decent enough job of mimicking them. Another thing that we've been working on recently is this problem that is a very old problem in consciousness science or in sensory science, and the idea that specific sensations contribute to your conscious experience, but they aren't the totality of it. So when you are experiencing the world, it's not just your sensation, there's a whole lot of other aspects that are going on. It's a problem with subjectivity. So, related to. The problem that we really have is how to separate changes in sensation from changes in experience, particularly during altered states, because altered states like taking psilocybin or LSD, or indeed under certain clinical conditions where you have hallucinations, are very informative about the distinction between sensation and conscious experience. So we set about trying to kind of make a hallucination machine, as we called it, that in some way mimicked some of the properties of changed sensation and hallucination. And to do so, we combined just a deep convolutional net again, and virtual reality in this case. This is all described, it's very large, in this recent paper in Scientific Reports, if you wanted to have a look more about it. So many people probably saw a while ago, 2-3 years ago now, when there was this big deal about Google releasing their visualization of different image classification networks, and it's called Deep Dream. And it's a bit hard to tell here, but what we have here is the original image, and there's a market scene at the University of Sussex, and then we have each of the different deep dreamed outputs. And the key here is that when you apply the deep dream algorithm, you can execute it, you can stop it at particular layers in the visual hierarchy. And by doing so, you can capture on the image more and more complex features. So you can see here at the lower level, we've got these very swirly, very primitive distortions, while at the top you have these very object-oriented distortions. This video. And so what we did was we did deep dream in the way that I just described on these videos. And then we had it in a panoramic view. These were panoramic videos, and we showed people these panoramic videos through an Oculus Rift. So basically they could move 360 degrees through the scene. You can see there's lots of distortions. Okay, and so what we have here is some polar plots. The grey here indicates when we just showed the video without any modification, while the blue shows when we had these modifications. So these are the subjective ratings of a set of participants to these questions that have all on the bottom. So these are questions about how it feels to be watching this thing. Over on the right, we have, again, the same responses, or similar responses, about watching this video compared to when people were actually taking psilocybin and reporting about that. So this is a phenomenological questionnaire, and then we're looking at how the responses are distributed for normal video, a weird video, and weird video versus actual weird hallucinatory experience. And so, at least in principle, you can see that whilst watching the hallucination machine, people's subjective experience was quite different from just watching the regular video. And maybe not so different from when you're actually visually hallucinating. So that tells you one of two things: either our machine's really good, or this questionnaire is not really good at capturing subjectivity. But that's okay. And in the paper we link it a little bit to this discussion about the idea that visual hallucination might be to do with different kinds of visual hallucination, might be to do with different kinds of changes and alterations in sensory classification networks. And if you have distortions in lower levels, you're going to get geometric hallucinations. If you have distortions in higher levels, you might have fully hallucinated objects and so on. I'm apparently out of time, but I can just say very briefly, we've been using it for data analysis also. We have these huge data sets that we get from EEG and fMRI. They all, like this. It's these huge volumes of data. And it's a real problem because humans aren't good with statistics or numbers or nonlinear relationships. And so we're not very good at analyzing these kinds of huge data sets. One of the classic cases is this kind of mismatch negativity. They refer to it as a system expectancy-based thing. So we can have a long string of identical things and then an odd one out. And all we've shown recently is that we can use these classification methods to decode these binary states, whether it was an expected state neurally or an unexpected state. And by using these multivariate methods, we can then extend into using generalizations. So these are just generalization matrices across time and across different conditions that show that we can extract this information that's available in the brain about whether the same physical stimulant is expected or unexpected. And that's detailed here. So that's my quick overview of the stuff I've been doing.
Thank you. Well, I forgot to say something quite important, which is the actual structure that we're going to follow tonight. Sorry about that. So the three panelists are going to do the same that work thank you, just did, which is do a short presentation. There is not going to be Q&A session right afterwards its presentation, but we're going to have a combined open discussion. So the presentations are more also to transmit the latest research, but also to give you guys the opportunity to come up with ideas and questions and inputs if that's the case. So, well, let's welcome our next panelist, Grace. Thank you.
Okay, so as you can see by my title, I'm also going to be talking about convolutional neural networks and how they can be used to understand the brain. So, Warwick thankfully introduced these, but I'm going to speak about them in a little bit more detail because it's relevant to the work that I'm doing. So, yeah, so basically when you have a convolutional neural network, just to refresh people or for people in the audience who are familiar with this, essentially it's a series of simple computations that are done and done repeatedly, so the convolution being key. And so basically what happens here is that each artificial neuron in the first layer of this artificial neural network, its activity is a function of the weights of a filter times pixel values in the image. And so what happens here is that you apply this same filter all over the the image, and you get a bunch of artificial neurons with a bunch of different activity levels, and you can apply different filters and get different patterns identified. And then there's some pooling where you just take some of the activities from here and shrink how many units there are, and then you do the convolution again over and over and over. And so I'm explaining this because, well, one, because these are, as we know, very important for computer vision today, but also because the architecture is inspired by biological vision. And so what happens in biology is that you have the eyes, of course, where light comes in, and then that information eventually gets passed to the back of the brain to an area called V1. And the neurons in this area project to V2 and then V4 and IT. And as you go along this pathway, the size of the visual field that an individual neuron responds to gets larger. And so that's similar to this idea where this artificial neuron only responds to this area of the image, but then an artificial neuron in this layer would be responding to a much larger area of the input image because it gets input from multiple neurons in the layer before. So this feature of the visual system that was discovered, I guess in the 60s, that the receptive field or the area of the image that a neuron responds to gets larger as you go through the visual system, that's replicated in these networks. And then also the complexity of what the neurons respond to also increases as you go along this network. So it's known that in an area like V1, cells respond to simple lines at different angles. And then as you go up, you get things like edges and shapes, and then eventually full complex objects like faces. And so as we saw, the features that the artificial neurons later in this network respond to become more complex as well via this stacking process. So you can see that this was clearly inspired by what was known about biological vision, and it's replicated in this artificial vision. More than that even, these networks, once they're trained to do object recognition, they are currently the best models we have for predicting the activity of real neurons. So in this experiment, an artificial network, kind of like the architecture that was shown these images, which I don't know if you can make them out, but they're a 3D rendered object. In this case, it's a face, and then a random background is paired with them. And these images were shown to the network as well as to a monkey, and neurons were recorded from different areas in the visual system. And so then the question was, can you use the activity of the artificial neurons to predict the activity of the real neurons? And so what's shown here is in black, so each, on the x-axis, each dot is an image, and then in black is a neuron's response, so real neurons, and then red is the estimated response by using the artificial neurons to predict. And so you can see that there's pretty good accordance, especially these chunks are organized by categories. So these are all the pictures of heads, and this neuron likes faces, and so it responds a lot to that, and the model is able to capture that. And so, even more specifically, looking at different areas in the brain. So I said that the progress along this system, you go from V4 to IT. Here, this is showing if you want to predict V4 activity, which is kind of the second to last layer, you can think of it in the visual system, at least in this rendering of it, you use the second to last layer in this network, that performs the best. And if you want to predict IT, you use the last layer of this network. So there's a correspondence between layers in the network and areas of the visual system. And so people have kind of looked at this relationship and asked this question a lot of different ways, not just by predicting neural activity, but kind of other measures of representational similarity. And these findings hold this idea that you can see a match between the different layers in the network and the different areas of the visual stream. There's also a lot of research done to compare behavior of these networks to human behavior. So in this example, we know that these networks can classify images well up to human level accuracy, but in this example they're asking what happens if you degrade the images. So if you decrease the contrast of the image, it should be more difficult for humans to classify, especially in these experiments. These are shown usually very quickly. And so you can see that classification goes down as you degrade the contrast, and the red line is humans, and the blue lines are different networks, artificial neural networks, and so you can see that there's a similar pattern. So there's matching in the representation and matching in kind of more fine-grained behavioral measures. And this is if you add noise to the image. So kind of like pixel-wise noise, you see a degradation in both systems. So, so that kind of is the background for my research, because I kind of start from the perspective that these networks are models of biological vision. And as someone who does computational neuroscience, I'm interested in building models of the brain and kind of, playing around with them to see if I can learn anything about the brain. So the main question that my research asked was, can we use these networks to understand how visual attention works? And so there are different ideas of attention, both in neuroscience and psychology, and also machine learning. The word is used in many different ways. So I'm just going to give a quick example of what I mean here. This is just basically the idea that if you're told about what you need to look for, you're better able to find it. And so in this example, a subject would be given a cue, so they'd hear a word like pumpkin, and if they heard the word pumpkin, they knew that they were going to be asked if they saw a pumpkin in the image that was about to be presented to them. And alternatively, they could not hear any word, and then they'd be asked about something, but they won't know what. And on the trials where they're cued as to what they'll be asked about, they're better able to detect, and they can detect faster if there actually is a pumpkin in the image. And again, these are images that have a lot of noise over them, and they're presented quickly, and so it's a challenging task. And so being cued in advance about what to pay attention to helps. So to ask if the way that biological attention works can work in these networks, and if we can understand biological attention by using these networks, we have to know what biological attention is. And so that's what a lot of other people have done before me. And so basically, if you record from neurons during the type of task that I just described, what you can see is that neurons that like a certain stimulus, so this is the response of a neuron to different stimuli. Neurons that like the stimulus, meaning they respond strongly to that stimulus under normal conditions, will increase their firing rate. They'll be even more excited when that's attended. So their preferred feature, if their preferred feature is attended, their firing rates go up. Whereas if their non-preferred feature is attended, things that they don't normally respond to very much, they'll respond even less. And so to replicate this in an artificial network, basically I just had to find out what all of the artificial neurons preferred. And so if there's an artificial neuron that prefers pumpkin, so if I look at the activity, how they respond to different categories, and then I want the network to attend to the category of pumpkin, then I would just scale up the activity of the neurons that prefer pumpkins and scale down the activity of neurons that don't prefer pumpkins. So it's meant to just be a direct replication of what's found biologically in these networks. And so what I find is that indeed applying attention, so I'm applying this attention process at each layer in the network individually, and you can see that the performance on, it's a similar class of task of classifying an image as containing a certain category, not just like the example test that I showed you. And applying attention to this network can increase the performance on this task significantly. And applying attention at later layers in the network increases the performance even more, which is in line with findings in neuroscience that effects of attention are stronger at later areas of the visual stream. So to summarize, convolutional neural networks were inspired by the architecture of the visual system, and now they can actually serve as very good models of biological vision. And so starting from that, we can use them to explore a lot of different elements of neuroscience, and particularly visual neuroscience. And so this is kind of one way in which machine learning is helping neuroscience.
thanks a million, Grace. And we have the last presentation from our panelist from Tivity. She's going to talk about EEG and brain-computer interfacing.
Thank you. Hello, everyone. I won't talk about convolutional neural networks. So in my area of research, we try to apply both machine learning and neuroscience to develop practical systems. I come from a brain-computer interface and neuroengineering lab in Essex, which is under the Department of Computer Science and Electronic Engineering. So we are nerd, basically. And we try to use neuroscience and machine learning for developing these brain-computer interfaces. So first of all, let's introduce what is a brain-computer interface. Everyone familiar with this term? Have you ever heard this? Yeah? So you might have heard this as a brain-computer interface, mind-machine interface, brain-machine interface. They are more or less all the same thing. So they are devices that we can develop for converting brain signals into commands or decisions. And when we talk about brain signals, we are talking about detecting the neural activity of users or of a user using a different device, for example, electroencephalography. So, of course, I could talk about brain-computer interfaces for hours, so this is a very, very small summary about this. But the thing you need to know is that BCIs, brain-computer interfaces, have been generally introduced for helping people with disabilities to communicate or to control prosthesis, or in general for applied to rehabilitation or to restore some motor control from people with disabilities. And these devices that look kind of very futuristic, let's say, have been developed in the last, I would say, 35 years. In the recent years, the BCIs have also been used for trying to augment our performance. So one day someone woke up and just said, like, wait a minute, why do we need to use these very advanced technologies only with people with disabilities? We could actually not only restore motor functions, but we could also augment our functions, so perform better as a human. And this is what goes under the word human enhancement or human augmentation. And we'll talk about this a little bit after in my talk. So in general, what you need to know is that BCIs are generally composed by an EEG, let's say, a part in which we detect the brain signals from the user, and then there is the machine learning component that tries to extract patterns from those brain signals and converts into commands. They are not devices for reading your thoughts. This is one thing. We are not able to understand yet what you are thinking exactly. So the BCI in general is one of the best, I would say, examples of this synergy between neuroscience and machine learning. Neuroscience basically studies the nervous system, so it provides this type of basic basic knowledge about the brain, which is the motor, the engine of the BCI. And the machine learning tries to convert, as I said, like these brain activities into commands, but the machine learning, as we have seen in previous presentations, could also inform neuroscience, could also be used as a tool to analyze brain signals and to understand the brain. So the main aim for developing very advanced BCIs is actually to understand the human brain and how it works. We need this. We can't only rely on very complex machine learning algorithms there. We need to understand how and improve our knowledge of the brain. In general, when we talk about BCI, we talk about two possible categories of BCI. So there is one category which is called self-paced BCI, in which the device could be controlled by the user fully, and when the user wants to issue a command, just think about a specific brain pattern, a specific mental task. It performs a specific mental task, and the BCI is able to understand that the user is performing that mental task and convert that into a command. So this is usually the type of BCIs that you see for people with disabilities. So for example, you ask the person to imagine to move a limb without actually moving it. And the BCI is able to extract this pattern in the brain, from the brain, and convert it into command for a prosthesis or for a wheelchair. Well, another set of BCIs is so-called a Based BCI, where they require basically a computer or a screen in front of the user. And in these BCIs, you present a stimulus, you present could be a picture, a video, or a signal to the user, and what you do is getting the reaction of the brain to that particular stimulus. And then you can train the machine learning algorithm to see, look, if I have an event here, and I record a specific brain activity. If I change the event and I record a different brain activity, and this happens quite often, then I can say, okay, this brain reaction is associated to that event. And therefore, whenever I generate this event, if I see that reaction, I can understand the intention of the user. So at Essex we used both of these. In my research I had the chance to actually develop both types of BCIs. One of the things, so the first one, the Selfpaced BCI, have been used in a competition that we ran last year, which was called the Cybathlon, and was the first international competition similar to, I would say, the Paralympics, but in which like people with disabilities were competing against each other, but they were also helped by the technology. And there were 6 races. One of these was a BCI race in which we had a person with who was like paralyzed from the neck down that had to control a video game, obviously without moving any muscle, but just with the thoughts, with a BCI there. And the idea was that the user was looking at the screen and was controlling this avatar that was running on a path here, and whenever the avatar reached a specific platform of a certain color, the user had to issue a specific command. So the user was thinking a mental task, was performing a specific mental task for the purple platform and another for the blue, and so on and so forth. And this was done not in a lab, but in an arena in Switzerland, so with all the people cheering and noise, and people that know a bit about working with EEG and with BCIs, they know how these affect actually the type of signals you record there. So it wasn't an easy task, but was actually a great opportunity to push research into developing devices that could actually be used to help people communicate and control technology. The other part in which I focus on, and which my research is on, is actually augmenting performance of users. So what I do is basically try to use BCIs to assess whether you are confident or not when making a decision. When you make a decision, any decision, and I can ask you how confident you were in deciding. If I ask you what is the weather outside, maybe people that just came in, they are very confident in answering, the others do not have any idea. This type of confidence, we could actually extract that from the brain signals themselves. So a way to improve decision making in general would be, first of all, to decide all together and to take the majority. So if I ask you what's the weather outside, who says that it's raining, raise your hand, then I can take the majority of the responses and say, okay, this is our decision. But some of the audience will be more confident in this. And the idea here is to use this approach. So to use BCIs to estimate how confident you are when making a decision. And to just show you the type of decisions we are talking about, I have a very quick demo now, which is basically a very funny one. I'm going to present you a picture with an environment full of penguins, where there could be a polar bear. Let's avoid to talk about the limitations of this possibility because they live in different areas of the world, but just let's assume that they could stay together. So you will see this picture for a quarter of a second, and then you have to decide whether there was a polar bear or not. And it's going to be all on yourself with a big responsibility. So focus on the screen, you will see a fixation cross in the middle, and then the picture, and then a mask that will clear your short-term memory. Ready? So, how many of you have seen a polar bear? Where was it?
On the left image. On the left of the left image.
On the left?
Yeah.
Wes? You have seen? Middle. Okay. So in this case, if you take the majority, we would have failed miserably, because the polar bear was right there. But you see how difficult it is, this type of task for a single individual. So when we are talking about augmenting human performance with BCIs, we are talking exactly about this. About tasks in which as human we have limitation because of the limitation of our visual system, of our brain as well. And we are trying to use technology to actually augment ourselves. And when you record the brain signals across multiple people and across different decisions like that, you can actually see that it is possible from your brain signals to predict whether you are going to make a correct decision there or an incorrect one. So in other words, your brain knows when you are not sure about that decision, and therefore you are more likely to make a mistake in that decision. And what we do is actually using that to assess and decide who to trust on a decision by decision basis, like the one that we just saw. So I'm gonna quickly wrap up. So the first thing is about why BCI could do this type of job. When we link together neuroscience and machine learning, why can we predict something that we are not aware of? And the reason is a very big overview, so forgive me for the lack of details and accuracy here, but just to give you an idea, when we use BCIs and when we record the EEG signals, we are in a way able to see what our population of neurons are doing at the moment without having the conscious system coming into play, basically. So what we are doing is basically targeting the visual perception part of our brain, the one that Grace said before. So in the back part of the skull, of the brain. And the BCI is able actually to tap into this unconscious mind, and before having cognition come into play and filtering out some information that we may have perceived, the BCI is able to tap into there and make more reliable and more accurate decision just by using this machine learning component that is able to understand and predict if you are going to make a correct or incorrect decision. Now, this is all very cool story about new systems, but in BCI, whenever we talk about research and developing new systems, especially those that could augment human performance, we kind of face some problems, which are ethical problems. And this is my last slide for today, and I want just to stop here, and hopefully this will raise some questions for the open discussion later on. But basically, we have talked about EEG BCIs, so we wear a cap and we detected brain activity from outside. But obviously, when we want to achieve accuracy for BCI, we could also implant electrodes on in our skull. So are we all happy to have to undertake surgery to implant electrodes just to augment our performance? Or is it something that we can only use, for example, for restoring our ability or controlling the prosthesis? Then in that case, yes, but for augmenting human performance, I don't know how many people would be happy to have a surgery in their brain for this. Also, there is a part of saying like, if we use a combination of our brain and machine learning, and we augment our performance, when does the human end and the machine begins? Are we becoming cyborgs, or are we still human that are less likely to make errors, but we are still humans, so we are still in charge of deciding whatever we want to do. And in that case, if we augment ourselves and we make a mistake, do we blame the computer scientists that developed that machine learning algorithm that made us make a mistake, or is it still our responsibility in that mistake? So these are open questions. We don't have an answer yet of this, but they are still parts in which we need to take into account when developing new systems and linking together neuroscience and machine learning. Thank you.
Thanks to the three of you for the presentations. Really great insight about the topic. I need to make a shout out because I know there are people who are experts on different fields related to machine learning and neuroscience here in the audience, and I will probably point towards you if, at some point, if I see fit. So I would like to start the discussion with something that I found quite evident while I was talking and the both of you were talking, which is we've talked about convolutional neural networks, we've talked about visual cortex quite a bit. I was wondering if it's because it's a part of the brain that we have more insights about. It's something that we can relate to quite easily in terms of we can transform those matrices of data into an image and we can understand that in contrast with other kind of stimuli, or it's just because it's a part of deep learning that is more developed. Yeah.
It definitely is the case that vision is a very big topic in neuroscience. A lot of neuroscience, especially like basic neuroscience research, not the medical side, is about vision. And a lot of the primate brain is devoted to vision. Partly, due to the importance of vision in primate lives, it's studied a lot, and partly due to kind of historical accident and kind of ease of manipulating the stimulus, presenting an image, and that kind of thing. But the same procedure that I talked about, where you record from neurons and try to use an artificial neural network to predict their activity when shown the same stimulus as the network, that's been done for auditory processing. And you use a convolutional neural network for that as well. So it can be kind of ported to at least auditory processing pretty directly. But yeah, and then any other kind of area where machine learning does well, like speech processing, there actually, in my opinion, there's not as much neuroscience there to compare it to because it's hard to study speech in animals. So I think it is about where the neuroscience is focused and also where machine learning does well.
If any of you have a question about the presentations or this topic, yeah.
So I have two questions. One for Tivity to start off with about brain-computer interfaces. So I actually implant invasive deep brain stimulus because I work as a neurosurgeon. What I found is quite a lot of this EEG information that we get is actually not accurate enough for us to be able to do our surgery. For example, if we're looking for where epilepsy is coming from and it's very deep inside. But I'm sure we're like 10, 15 years behind the research labs and what you're doing at the moment. In terms of the technology we have for brain-computer interface at the moment, is it only accurate for picking up information that's on the superficial aspects of the brain, if we're talking about EEG? Or are you able to now pick up quite precisely signals from deep within the nuclei of the brain, so very deep brain matter? Because I can imagine as you go deeper, it gets harder and harder to get clean information with a lot less background noise. Where are we at the moment? Can we replicate that?
Yeah, thanks for the question. We are still behind. I mean, the EEG is still one of the most used techniques for observing the brain activity used in developing BCIs, and the reason is because it's much cheaper than other technologies, could be present in every lab. So yeah, I mean, the EEG, I understand, is not the optimal technique for observing in terms of accuracy, in terms of also the, how can I say, the resolution that you can actually get from it. So we are not able to, for example, understand if a neuron is firing or not. We are not able to understand if a small group of neurons is firing or not. We are targeting areas of the brain. We are targeting big population of neurons. We also require to collect a lot of data and average this data before being able to identify these patterns that we have seen before. So I'm not hiding the fact that the EEG is way away to be perfect and requires a lot of more, let's say, research in how to project artifacts, for example, or work in an environment. But at the same time, EEG could be literally used in many situations and with everyone. So if I had an EEG cap today here, I could plug any of you and record signals already. When we talk about other metrics, like other measures, like fMRI, we need a bulky room for that. If we talk about invasive techniques like implanting electrodes, I can't implant an electrode today on any of you, I think. So obviously there are pros and cons of using EEG, but at the moment I would say that still there is a big push in using EEG for BCIs, and there is a big push into trying to develop both algorithms that could clean the signals that you get and other way to measure the brain activity, which are in between the invasiveness of implanted electrodes and the non-invasiveness of EEG. So you can still go under, just a bit under the cortex, and you can still get much cleaner signals than using EEG. But yeah, I mean, I think that this answers your question, I hope.
It does, yeah. Thank you very much. Can I ask you a second question, just to Grace? It's a very quick one. Your models were really, really impressive about how you replicated the visual pathway, and you said, you know, the model that you developed was the most accurate replication of what you see in primate brains. I was just wondering, if you actually, does it replicate if you have an injury? So let's just say you were to cut the neural pathway somewhere down the line, like in somebody's head or an injury. Does it replicate that quite accurately as well? Is it literally the best representation we can get?
So it's the way in which it's the best representation is for a particular period of time after an image is shown, if you average the activity of neurons for that time, it can predict that activity. But the response of neurons to images changes over time, and that has a lot to do with connections to other neurons at one area, and also feedback connections from areas later in the brain. And so people are trying to capture that with these models, but it doesn't do that yet, and depending on where a lesion would be, it would probably be impacting feedback, or it could be impacting lateral connections. And also, in the simplest version of this, it's just the layer below connects to the next layer, which connects to the next layer, but in the brain you can get V1 to V4, and so that would also impact, you know, modeling of that kind of detail. So right now, I don't think that it would be the most accurate way to represent certain lesions, just because there wouldn't be a way to implement those lesions accurately in the model.
Thank you very much.
So I would like to link what you were talking about before of augmenting the human being. The piece of research that you showed about hallucinations, I think is really, really interesting, especially, well, that would be a way of enhancing somehow human, human sensory, or how we integrate them. Do you have any more examples about that kind of topic, like using machine learning to enhance our senses?
No. I mean, so this is very new, right? The work which Grace mentioned a lot of, which is the last few years of people kind of showing the similarities between visual cortex, not of this close. When we look at the literature on this, it's only over the last few years that people have really made this strong connection between of course it's inspired by biology, but the validation that, you know, this does have many of the nice functional and architectural properties of visual pathways in primates. That needs to be true before you can start tinkering. And I guess this goes to the lesion point as well. You know, we have to create that initial condition and then start tinkering in it. And I mean, still, many people find it very controversial, the degree to which it is a reasonable functional analogy. So the degree to which we can extend on that depends on the degree to which people will agree about it. And a lot of my work, as you saw, kind of in some way pushes past that, and you say, well, if we assume that there's some kind of functional analogy here, the degree to which it works is the degree to which it works, and that's the degree to which our analogy works, and that's the degree to which we can use it. So, you know, is that system that I'm showing you doing exactly the same as what a human does to estimate time? Of course it's not. Is it doing a reasonable functional analogy based on some reasonable base assumptions? Maybe. We can argue about it. So it's a hard place to be at the moment because we're arguing about a lot of the really important stuff, making it very difficult to do some of this secondary stuff that I'm talking about, and that's totally fine. I mean, where these are our tools, they're not very good.
Thank you. Any of you have any questions? Yeah. So please don't be shy and just raise your hand.
Hey there. So moving away from the specifics to a bit more of a broad question here, an open one to the panelists, and I guess anybody in the room. At what point should neuroscience stop informing machine learning? What is there to say that artificial intelligence should look like human intelligence? And if we're going to pick and choose, what framework can we devise as a way to work out what aspects of the way we do things is a feature and not a bug or a limitation of our evolution?
I would say that it's always up to the person who's making the AI and the specific use case that they have for it. With vision, the goal was to get to human level performance, but now the performance is, by certain definitions, surpassed human level. And if you just want to analyze a bunch of images, you don't care if it makes the same mistakes that humans make. You just want to know what kind of mistakes it makes if it makes mistakes. So, yeah, there's plenty of use case for artificial intelligence that doesn't work like humans and doesn't mimic human behavior. I think there is, though, an inherent drive amongst a lot of people who study AI to replicate and to replicate the complexity and the ability to do multiple different tasks, even if you can't do any of them so great. But that's just a different research question than people who are focusing on more specific things.
I think that there is another main difference between using an AI to perform a task and using a human. So they both talk about convolutional neural networks, and one of the amazing things you can do with convolutional neural networks is actually to improve the human performance and outperform a human quite easily in many tasks, I would say. Now, one of the problems of convolutional neural networks is that they require a lot of data for training. So you need to teach the neural network how to identify that particular pattern in image. If I show you an image with a bunch of people, then we have algorithms that they are able to extract faces, to compare faces, and all of these things. But if I show you something which is not very structured, so and I ask you to actually identify that particular object, you still need a lot of data for training the artificial intelligence to do it. While a human generally with just one image is able to identify similar objects. So we did a bit of research on this recently, and we tried to actually do the task that you have seen in my presentation before about identifying a polar bear in a picture, and we asked an artificial neural network actually to extract polar bears from pictures and identify whether in an image there was or not a polar bear. And we found out that on average, like when you average like 300 or 400 decisions there, the neural network performs as a human, as the average human. And whenever you put together more humans, they act as a group, they could still outperform neural networks. So we are not, I wouldn't give for granted the fact that artificial intelligence is always ahead of humans. We still need to develop it, and I would say that we still need to identify which tasks we don't want to perform as humans because they are boring or because we simply can't achieve the same performance as a computer, and which tasks we want to take on our hand. We want to perform ourselves, maybe aided with the technology, but we don't want to give them to an AI. And there is a lot of discussion about other things on this. I mean, it's not easy to answer.
I just wanted to add in as well. I think the reason for framing AI in terms of to be human-like or looking to neuroscience for inspiration is in large part just due to the fact that brains are the only thing that we know that can do the stuff that we want computers to do. And I think that that's a very reasonable idea to have and a reason to follow the neuroscience path. But then the exact details of the brain, some maybe are just constraints of evolution and constraints of being a physical body that aren't relevant. And so the teasing apart what's the relevant implementation details is a real question. Even if you want human-like behavior, you might not need to replicate a brain in detail.
I'm not going to add anything of my own here, but I was at a meeting recently and Jan Kuhn was one of the keynotes, and his comment was really good in that image classification networks are inspired by biological vision. They work well. That's great. There's not very many other examples of any kind of artificial system working well when we've gone in that direction, and we haven't been very successful in that way. And he brought up the case of, when you talk about flight, 150 years ago, people were building flying machines that looked like birds, and that didn't go very well. And then we built fixed-wing things that look nothing like biological, not nothing, but they don't resemble very closely the mechanisms of biological flight as we understood them at the time. Of course, now we understand more closely that they do at a very micro scale rather than the macro shape. And that was a waste of everyone's time, building these flapping bird machines or things with bat wings that didn't work out if you wanted to build flying machines. So not to get too caught up in we should only ever find inspiration in biology for artificial systems or vice versa, like it's horses for courses. If something is a useful strategy and is working, of course pursue it, but don't do it to your own detriment.
And I suppose we need to fully understand the biological system to understand its limitations and not to include that in whatever we're building.
Yeah, and so that feeds onto Grace's comments and Grace's comments to the earlier question, of course, which is, we know a lot about biological vision. We've been able to study it because we can go into primates and stick electrodes into single cells and map it out, and we were able to do that 60 years ago, 50 years ago. And now we're able to expand that into more modern approaches and have computational models that are built on top of all of that, whereas for most other cases, that's really, really hard to do. So how can you draw inspiration when we don't even know how things are working to begin with? I assume we'll go into black boxes later.
It's also a trap that I think computer science tends to fall quite often from my side, which is we try to mimic or to implement metaphors, right, all the time. Sometimes we struggle to come out of that metaphor, so this works in nature, so we go that way. There was a gentleman at the end that wanted to ask a question, I think. Yeah.
Thank you.
So I just wanted to probe the intuitions of the panel, including you, Javier, on whether, as intelligence of systems increases, does consciousness come along for the ride, or put another way, can you build a system that is intelligent as a human in every aspect that you care to name, that is not conscious?
I suppose the guy with consciousness science and has to respond to that. Yeah, we don't know anything. So define consciousness and define intelligence and define any of these things in any system, and then we can talk about it. I mean, this is the big challenge right now, and really there's only one game in town in trying to do this, and that's integrated information theory, and anyone who's been tracking that in its progress knows the difficulties that it's encountered. So it's not really, we're not really in a good space to answer that question at all because we don't have a definition of consciousness. We're not really sure what intelligence is except in certain circumstances as well. So can we have a machine with intelligence without consciousness? Probably, because we just make up those definitions that it doesn't have one and does have the other.
So there was another gentleman at the back that wanted to ask a question.
Thank you. Excuse me. First of all, I'd like to congratulate you. All made some excellent presentations because, first of all, the title of the event really sort of inspired me to come in and say, because I wanted to see what the connection between AI and neuroscience. And I don't have the question clearly defined. It's really more exploratory. Let me just set the stage here. There is a great threat through cyber on us all. And I was wondering with the research that you've come across or you've been engaged in or with stuff that you've learned, do you see any value in some of what you've learned that could be utilized today to mitigate the threats from, let's say, cyberterrorism, political hacking, and stuff like that? Because at the end of the day, they do relate to the way the brain operates by some of these bad actors. Secondly, there's a component in everything to be done that could be placed in the hands of the good actors or the bad actors. So, if you've come across anything like that that you think can be of value, not 5 years or 10 years down the line, but today, because the threat is today, then I'm interested in hearing a bit more. And one last thought on a light-hearted note, putting probes in somebody's heads. I'm not quite sure, would you be able to put one or some in Trump, perhaps, stop him from tweeting more and maybe getting closer to the nuclear button?
So, well, I think it depends on what is the aim here. I mean, if the aim is to understand what happens in Trump's brain, then there could be like a...
I should have started with the Trump question first. That was like a joke, but the first part of the question was serious.
Yeah, no, I understand. But again, I mean, this answer applies also to the first part of the question. It depends what is the main aim at the moment. So obviously we can apply BCIs and the type of research I presented before also to surveillance. We can apply it to counterterrorism. We can apply it to many different areas to increase our safety and to detect potential threats. And this is already applied and kind of research as well. I mean, even if you go through an airport, you don't apply BCI, but you apply artificial intelligence when you're scanning your suitcases over the X-ray. So we are still using technology to help us in doing our task and in this context. Now, the threat of cyborgs, though, is a different thing because when you use BCIs, you actually are creating cyborgs. You are creating humans that are using BCIs to improve their abilities. If you are using a BCI to restore the ability of moving a limb in a person with disabilities, in a way you are still creating a cyborg. Because, of course, this is isolated a bit from the computer science part and goes more towards ethics and more this type of philosophical, let's say, question, I would say. But still, we have to take fix in our mind the fact that whenever we apply technology to augment our performance in any context, we are creating cyborgs. Now, there are good cyborgs and there are bad cyborgs, of course. Of course, everyone would agree here, saying like, as long as we develop good cyborgs, we are fine with technology. But then we will still face the threat of having this technology applied by bad people to a bad cyborg. So that's why we need to be cautious here. We need to remember that every technology that is a BCI has still the human brain in the loop. So the human brain is still the one that provides information, provides input to the system. And as long as we keep the human in the loop, we can still claim and we can still point the finger to the human that wanted to do that particular task or that particular action. Whenever we talk about artificial intelligence only, then everything becomes a bit more fuzzy, because what is the problem there? Is it that the artificial intelligence learned too much and learned to behave badly? Or is it the programmer that programmed that artificial intelligence to do badly? Well, as you may have understood, I don't have an answer to that question. It's not an easy...
I didn't think there was an answer.
But I just want to kind of share my thoughts about these topics.
I only know very roughly about this, but it's more in your field, but this whole neural lie detection stuff that's been going on. There's lots of companies, particularly in the US, that are selling neural lie detectors, and they're completely bunk, and they're incredibly dangerous because people are basically, you go and just like old lie detectors based on physiology, you can beat them or not. The false positive rate's high, the degree to which it's sensitive to anything is immensely debatable, and this is really, really dangerous. So that's one really problematic area that's in that direction, that you're kind of saying what things can help us. People are looking out for these things now, and they're finding answers, but these are not good answers, and they're very dangerous things. And people
if I may just put something in perspective, and I'll give the microphone to somebody else. The concern I have is, while we are in this room, we're always around intelligent people. Intelligent people who are focused on doing good. The bad actors who are also intelligent are also finding ways to apply the same, whatever can be discovered, for bad purposes. And we are in a race. It's a war zone out there. And the concept here is, if this is something that could be explored, is to see what can be created or leveraged so it becomes something that could be utilized for better defending us. That's what I was thinking. Because if it's available, the bad actors will discover it and they will launch it and they will use it. That's the point.
But presumably any such tool would then be available and would just be another cycle. The answer is right. So, I don't know.
Part of the thoughts. Thank you.
So I want to ask, to link what David and we're talking about. So trying to make a lie detector is a little bit complex because we don't know that much about the brain in terms of, well, if you put an electrode and you try to say, okay, that's a lie, you're going to fail, because first we don't really understand what's going on inside, right? On the other hand, we are relying on these algorithms that they have 1 million neurons that we have trained for 2 weeks and they seem to work, but we don't really understand what's going on inside. And we're trying to link here like two black boxes, and we're trying to understand a black box with another black box. So that sounds like a lot of noise to me. So do you have any thoughts about how we mitigate that, or how to prevent this noise to darken all the research in these areas?
Well, first of all, I mean, for creating a neural lie detector, we can't use, I would say, supervised machine learning, because that would require asking a person to tell a lie and never knowing if that was really a lie or was a lie about a lie. So this is one of the main limitations whenever we develop BCIs which rely on supervised machine learning. We expect our users to tell us the truth about the task that they are performing. With the lie detector you can't. What you can actually do though is to integrate, so to use not only neural signals, but to integrate other physiological measures that have been used in the past for lie detector. So, for example, to detect like the pupil dilation or the skin conductance or other type of measures that you get from the body, and integrate all of them with the neural signals, then maybe they could kind of fix this type of noise that you have in the EEG. But I would be interested actually into looking into how a lie is mapped into the brain, and what is the signal that you record whenever, if there is any, that you record whenever the person is telling a lie, is telling a lie.
So I think you can use the lie detector notion as kind of a way to talk about what a black box is. So if you take brain activity and you build a machine learning algorithm to try to detect a lie, if that machine learning algorithm is a neural network, isn't super relevant to the neuroscience machine learning comparison. This is like a data analysis use of machine learning the same way it's used in genetics and other things. So the fact that it's a neural network is not relevant. It's just an algorithm to try to read something out from the data. In the case where you're actually comparing artificial neurons and their activity to real neurons in a way that's meant to imply that the architecture are the same and this is the process that generates the neural activity, I don't think that you're treating the neural network as a black box anymore. I think you're opening the box and you're trying to understand how it works, and you're looking at the activity at different layers. So it is the case that the vast majority of times that neural networks are used in artificial intelligence and machine learning, they're not probed. I don't think they're just used, and if they work well, that's great. But in some of the cases that they're applied to neuroscience, they're not used as a black box, they're used as a model.
So we have time for one more question. Yeah.
I just wanted to make a response to that.
It occurs to me the lesion idea is, we know most of what we know about the brain is from lesions, and so having a neural network black box that you could break would turn you kind of reverse engineer it that way. So does that make sense? I don't know, if you have your neural network and you can introduce artificial lesions, and then you can work out in the same way that we work out how the brain works.
Hi. I don't know if my question is about to reveal a fundamental ignorance of both AI and neuroscience, but has there been any advance towards the ability to map visual memory, so actually be able to see images that people saw long after an event, or is it right now for any things they have directly in front of them at that moment?
There's work about, so one way to answer that is that there's a lot of work about the ability of people to recognize images, even if they've seen them once and they've seen 1,000 images in a row. If you show them another 1,000, they can fairly accurately say, like, yes, I saw that one, no, I didn't see that one. And so there's studies that look at when you re-show the same image, how is the activity different than when you're showing an image that they haven't seen, because there's something surprising about that memory capacity. There's also work about having people visualize things and see if you can read that out. So I think that's kind of, you have to have some trigger that would put the memory in their mind if you want to be able to read out a memory. So I think visualization and re-showing the same thing are the ways that that's looking.
Yeah, just to add to that, it's just, as Grace mentioned, so you can just have someone see something and then say, imagine this later. And the basic weightings you've got in your decoder, in your neural network, whatever, that you've got for the actual image will decode the imagined image relatively well. So if you say, remember the front of your house when you were growing up, and you show a person a picture of it, the brain state that you have when you are viewing that picture will decode the imagined picture quite well. So the degree to which visual imagery is decodable, yeah, the degree to which that's related to memory is more complicated.
Okay, thanks. So, this is coming to an end. I really hate it because I'm having a blast with the discussion. So, just to wrap up, I would like you to ask you guys, in 30 seconds, to state a piece of research that you've read recently, or an idea that you had recently that is exciting you, just to share with the community your enthusiasm about neuroscience and machine learning.
I had to think about it. Well, I would say that, I read a lot of very interesting research, but I think that the main one is to actually be able to get the same accuracy in getting the neural signals that you get with implanted electrodes, let's say, getting the same accuracy with non-invasive techniques. So I think that we should push a lot this branch of research that is actually hardware research. So we need to create sensors that are able to let us get inside of the brain from the outside without requiring surgery. And there is a lot of research here in London about getting inside the brain from the ear and getting some EEG activity from there, which could be used also for targeting the temporal lobe, which is an area of the brain, and other parts. But basically advancing with the sensing, I think, the sensor that we can put on the brain.
I've kind of shown or provided evidence for the notion that these networks are a good model of the visual system, but obviously there's a lot of areas where they don't line up. And even in one of the examples I showed, when you add pixel-wise noise to an image, the behavior of the neural network is actually different from the brain. And there are certain ways like that the network's different. One specific paper I was looking at was about how these networks generalize and their ability to memorize. So basically you can train a network the same way you normally do, but instead of providing the true label for an image, you can just pick a random category for every image. You can say this picture of a dog is actually a boat, and this picture of a dog is an apple. And these networks, if they're trained well enough, they can memorize these random labels, which is, it's bad, because that's not what you want them to do. You want them to be learning actual categories and kind of things that make something a category. So their ability to memorize, you know, thousands and thousands of random labels attached to images is interesting, and there needs to be things about the brain that make us not do that. Kind of regularization is the idea, and so just kind of thinking about how you can add in more details from biology to make these networks kind of better behaved, and then also better models of the biology is kind of interesting.
One thing that's interesting about everything that we talked about today, we're talking about machine learning, as pointed out multiple times, we're mainly talking about image classification networks. And of course, the last few years has been a good development period for memory, all things approximating memory, right? So things like LSTM, you know, the development of making these so much more effective than they were before. One, it's a bit old now, but I think there was another paper recently that said this idea that you can take these classification networks and you can give them their labels and then basically give them a buffer space and they can start to solve kind of second order problems. So there was the one about you know, mapping the London Tube, for example, instead of having cognitive maps. Well, you know, it's trivial to us that you drop us somewhere in the center of London. Most of us have been around some of these streets before. We know, like, okay, I need to get to that place, so I need to turn right relative to my body and walk 500 meters. So we have these quite strong cognitive maps of how things are laid out in the world, and trying to mimic how those things can work in artificial systems is coming along quite well in a very rudimentary way. And the biggest challenge, I think, when we talk about neuroscience and machine learning is trying to understand human memory, because human memory seems to be the biggest kind of, it's almost everything. We won't have these questions about consciousness before. We're almost entirely the sum of our experiences, right? And every single thing we do is interpreted in light of those, and we don't really have a good comprehension of how that works. And making effective intelligence, that seems to be the biggest, effective artificial intelligence seems to be the biggest barrier, like having information in a useful way that can be brought up. You know, I did this experience in this time that these features were present. I was in this place, you know, all this huge amount of contextual information, bring it up and having it available in a kind of generalized workspace for you to manipulate and compare and then put it through some kind of inference machine or even some kind of classification, just to say, here's my decision tree, let's push it through. That seems to be the biggest challenge, and some of the recent work in DeepMind has been getting at some of those things in a very rough way, and I think that's very exciting. I look forward to seeing how that turns out.
Okay, great. Well, big thanks to you guys. It was fantastic, and big applause, of course. Okay, so this is coming to an end. So I would like to do an announcement of a BCI that is happening which date exactly?
Yes, it's the 27th of February is the next one.
Great. The 4th of February we'll have a hackathon in Neuroscience. We're developing this small time. So we're creating a small BCI that you can connect to your smartphone and then play with the technology. Yeah. So this guy is really cheap, 20 quid, and we hack together and we have a great time on a Sunday morning. So you're all invited to come and join the TEDx. Any more announcements?
Not just thank you again very much for coming tonight, and now please feel free to stay in the space, network, there should still be some drinks. Yeah, and just thanks for coming and hope to see you next time. Bye-bye.